What was the topic we were discussing in the last class? Where did I stop? What we were discussing in the last class, ma? Any one of you? We are discussing on the power efficiency of the different modulation techniques, AM modulation schemes. Am I right? The power representation for the double sideband suppressed carrier, it was found as depending upon only the suppressed carrier. Carrier is suppressed, so no need to calculate the power carried by the carrier. You are bothered about the power carried by the sidebands. So the sideband powers are going to be MA square V square by 8R and another MA into VC square by 8R. Substituting that, you will be having the total power carried. And if MA is equal to 1, accordingly, you will be having 0.5 times the carrier power. So that is the amount of carrier power needed for transmission. And how much amount you save is going to be 66.7%. Suppose if you go for the single sideband suppressed carrier, what is going to be the scenario? So in case of a single sideband suppressed carrier, you are going to transmit only one of the sideband. You are going to suppress the carrier as well as another sideband is also removed, and only one sideband which is going to have the information is taken. So by doing so, what is the performance or efficiency or the power required for transmit your single sideband suppressed carriers? You are going to have only either power due to the upper sideband or lower sideband, whatever it may be. It is going to be MA square VC square by 8R. So the total power required for transmission is going to be MA square. Instead of VC square by R, you substitute it as. So how much amount of power is saved when you are going to choose this single sideband suppressed carrier? If you make the substitution with the total power minus the single sideband power divided by total power, it will give you the amount of power saved. Amount of power saved is given by this expression. And of course, in this substitute MA is equal to 1, which is the critical modulation. So it will be 5 by 6 into 100. So it is 83.33%. So you have seen that double sideband full carrier is going to have power saving about 33.23% one. When you are going to suppress the carrier alone and transmit both the sidebands, it comes to 66.66%. And you are going to have your modulation index to be 1, and you are going to transmit only one of the sideband, then the power saving is going to be in an excellent way. It is going to be 83.33%. So this SSB-SC power saving compared with the DSB-SC, you can compare this by having the power which was due to the suppressed carrier is MA square PC by 2, and you are going to have the single sideband suppressed carrier power denoted by P double dash. Now we are going to compare these two powers. So how much power can be saved when compared to the double sideband suppressed carrier and single sideband suppressed carriers? Of course, transmitting 2 is going to be having more power required for transmission, or the efficiency is going to be poor. Half of it, only 50% you are going to save the power. So just make the substitution of the both the power, suppressed carrier power and the due to double sideband and single sideband divided by the double sideband, will be having power saving between these two scenarios, double sideband suppressed carrier and single sideband suppressed carrier, is going to be 50%. You are going to save up to 50% of the power. So what is the advantage? Why we go for this? So it has got many major advantages when compared to the first two scenarios, because in the first case, the carrier which doesn't have the information is also transmitted where the power is based. We base most of the power. So here suppressed side, the single sideband is going to have more power being saved. So only one sideband is being transmitted. So only one sideband is transmitted. The bandwidth required is going to be in this case FM only, not 2F. In the previous two cases, it was 2FM. And due to this, you are going to have a better signal to noise ratio that is going to be 9 to 12 dB. Fading can be reduced. What do you mean by fading is if the distance increases, the signal strength is going to reduce. So the receiver can't receive the signal properly. So the signal strength deteriorates as the distance increases. This process we call it as fading. And of course, it is going to be less expensive. Interference with the other channels can also be avoided. So these are the major advantages of your single sideband suppressed carrier signal. What is be the drawback there? So the main drawback is the transmission as well as the reception becomes more complex because only one of the sideband information is transmitted. Carrier is also not transmitted in this case. So getting the carrier signal as well as the uh, carry information signal, without these two things, receiving that such a signal is going to be a complex process. And carrier is also reinserted at the receiver end. So that is an additional feature we need at the receiver part. And it is going to be complex to design highly selective filter. So this filter which is used at the receiver side should be having more sensitivity for even for a less amount of signal. The receiver should be able to pick up the signal and demodulate it. So that becomes a complex, that design becomes a complex thing. Yes. And where we go for the application of this is going to be police wireless communications, telegraph systems, radio telephone communications system, and your very high frequency and ultra high frequency communication systems. In these ranges of communication fields, we go for your single sideband suppressed carrier signals. Okay. And we have to see one more modulation technique, which is called as vestigial sideband system. So what is vestigial? Vestigial sideband is you are not going to transmit both the sidebands fully. You are going to have a part of the sideband from the upper or the lower, and one of the sideband is going to be fully transmitted. So that is the scenario followed in your vestigial sideband system. So next type of modulation in your AM system is going to be vestigial sideband. So the main purpose of using a single sideband suppressed carrier is you are going to have the reduced bandwidth as well as the power saving when compared to the double sideband suppressed carrier. Just now we saw that comparison, how much amount of power is also saved in the previous scenario. So in a single sideband suppressed carrier, signal generation is very difficult in nature due to the selection of the desired sideband. So just now we saw the disadvantage of that single sideband also. So selection process, the selectivity of the receiver is going to be more. You need highly sensitive device to select the signal at the receiver end. So these two problems and also the designing of the filter is going to be a problem in the single sideband. So to overcome all these problems which is due to single sideband, of course it has got a reduced power bandwidth as well as it saves more power. It has got these disadvantages. To overcome these disadvantages, we go for this vestigial sideband. So what is vestigial sideband? Is you are going to have any one of the sideband to be fully transmitted, and you are going to have a partial of the other sideband. So how it is selected is you are going to have a very low frequency. You are going to have the lower sideband fully, and the high frequency component, there is going to be higher frequency upper sideband. There you are going to choose which is very close to the carrier frequency and also the sidebands. So you have to choose the signal in such a way that you are going to choose one of the sideband fully, another sideband is partially chosen. So So that way of communication, the partially chosen sideband should have very high frequencies. So you are going to choose it from the upper sideband. And all the low frequency components of the video signals contains most of the information is going to be in the picture form, which is going to be available in the lower sideband. Okay, so you are going to have, and you are going to have the complete suppression of the lower sideband results in the loss of information and hence produces distortion. So you have to take lower sideband, and we will show this diagrammatically. You can see that you are going to have the upper sideband and your lower sideband. This is the spectral diagram. This is the spectrum of the message signal. The message signal is band limited between FM and minus FM, whereas this is going to be the carrier. So full upper sideband you are going to transmit if you are going to have this. This is going to be the lower of portion of the lower sideband being transmitted. So this is how you are going to select in your single sideband. You are not going to have the both the sidebands being fully transmitted. So in that case, what happens is you are going to have the transfer characteristics of the filter being drawn. So this is going to be the transfer characteristic. This is the maximum gain of the system, and you are going to have suppression of your upper sideband. So this is the suppressed value, and this is the portion of the LSB being transmitted. So this part you transmit, and also you are going to transmit this part, and this is going to be the suppressed part, which is going to be near the carrier frequency. So FV stands for the vestigial frequency. So normally, so far what we have seen was the modulating signal frequency and the carrier frequency, which was denoted as FM and FC. Now we are bothered about the frequency which is going to be closer to the carrier frequency FC. So closer to the carrier frequency FC is taken as your vestigial frequency. So you are going to suppress a part of your upper sideband. So you are going to transmit a small portion from this and this entire portion of the upper side. So what happens to the bandwidth case? So bandwidth is normally difference between two voltage levels, upper sideband and the lower sideband voltage levels. So here this is carrier minus FC minus FV. That is the carrier minus the lower frequency plus carrier plus the lower frequency. And here plus the lower frequency becomes this frequency, FC plus FM. And with respect to this FC plus FC and FC minus FC, so substituting this, will be having the bandwidth of this to be FV plus FM, not either wholly 2 FM or partially FM. You can see the bandwidth is going to be in between. So it is going to be FV plus FM. So bandwidth of the vestigial sideband is going to be the bandwidth of the message signal plus the bandwidth of the vestige. Vestige is the small portion which we are going to transmit, which has got all the low frequency component information in it. Obviously, it is going to be the video signal. Fine. And filter characteristics, we have to find the frequency response. Frequency response, magnitude of the H of F of C. The response is going to be half of it, where this lies between two frequencies, FC minus FV and FC plus FV, and this exhibits an odd symmetry. Okay, and some of the two components in this range is going to be equal to unity. That is, transfer function of F minus FC plus H of F plus FC is going to be 1. And these are said to be the properties. Okay, phase response is going to be linear. What is the advantage of this vestigial sideband? First, you can compare with the bandwidth. Double sideband needs 2 FM, whereas single sideband needs only FM. So this is going to be in between. Compared to the double sideband suppressed carrier, it needs lesser bandwidth. And heavy filtering concept is not needed. Low frequencies are transmitted without any loss. You can transmit it without any loss. application is used in the television transmission since low frequency represents picture details and they are unaffected due to the vestigial sideband. So vestigial sideband advantage is going to be can be transmitted without any loss. So the main advantage is you are going to make use of it in the television transmission. So excuse me. So now we have seen what is AM, what are the types of AM available, like double sideband full carrier is your normal AM, how to get the signal, from the signal how to calculate the power, how to calculate the bandwidth. The same thing was done for double sideband suppressed carrier, single sideband suppressed carrier, and vestigial sideband. Okay, now we'll do few problems based upon your AM signal itself and also calculate the power for the AM signal. Okay. Just a minute. I will give you a problem so that you can solve it and give me the answer. Okay, note down this problem. For a AM double sideband full carrier wave, for a AM double sideband full carrier wave with peak unmodulated carrier voltage, with peak unmodulated carrier voltage of 10 volts, a load resistance of 10 ohms, and a modulation coefficient MA to be 1, determine the power of the carrier and the upper sidebands, total sideband powers, total power of the modulated wave, and also draw the power spectrum. I repeat, there is a double sideband full carrier AM signal with a peak unmodulated carrier voltage of Vc is equal to 10 volts. A load resistance RL is said to be 10 ohms and a modulated coefficient MA is going to be 1. You are supposed to determine the power of the carrier and the upper sidebands as well as lower sideband, and also the total sideband power and total modulated power, and also you have to draw the spectrum. So now, from the problem, what it is given is, let me open the notebook page that I can solve it. So what is given and what we are going to do. You are given with a carrier voltage of 10 volts and load resistance of 10 ohms. Modulation index coefficient is said to be 1. Okay, so these are the things. So the first step is to calculate the carrier power. So what is the carrier power? Carrier power is Vc square divided by 2R. So it is 10 square divided by 2 times the 10 value, or it is 100 by 20. So obviously it is going to be 5 watts. Okay. So this is the first. What is the second? Second thing is you are asked to find the sideband powers. That is power of the upper sideband, which is of course equal to power at the lower sideband, which is equal to ma square divided by 4 into the carrier power. Okay. So modulation index is 1. Carrier power just now we found it is 5 divided by, so 5 by 4 it is 1.25 watts. So upper sideband is 1.25 watts and the lower sideband is also 1.25 watts. So the third thing is, what is the total sideband power? That is upper sideband power plus lower sideband power. So upper plus lower sideband power is 1.25 plus 1.5 watts, that is 2.5 watts. Okay. What is the next thing they are asked? They are asked to say what is going to be the total power. What is total power? Carrier power plus upper sideband plus the lower side. So what it is? Carrier power is 5, upper sideband is 1.25, lower sideband is 5 plus 2.5, which is going to be 7.5 watts. So this is the total power needed for the transmission. 7. The other way you can calculate the power of the modulated wave. What will be the power? The other way of calculating this, instead of this formula, is total power is equal to carrier power into 1 plus Na square divided by. This is another way of calculating the unmodulated carrier power. So this is equal to 5 into 1 plus 1 by 2, or it is 5 into 1.5, which is also 7.5. So you'll be getting the same answer. So you can either go for finding the carrier power first step, then find the lower sideband, upper sideband powers, then add all the powers will give you the total power, or you can make use of this formula in calculating the total power. This will also come. So what is the last part of your problem is? Last part of the problem is you are supposed to draw the power spectra. So power spectra is going to be your y-axis in power, watts, and frequency in hertz. So how many components are there? There will be 3 components. One is the carrier component. Another 2 are the sideband components. Of course, you don't know what is the frequency because in the problem, the frequency is not stated. So instead, you generally write it as carrier power, carrier frequency, lower sideband frequency, and the upper sideband frequency. Carrier power is 5 watts. This is 1.25 watts, and this is also 1.25. So this is how you are supposed to solve this problem. Okay. Next is another problem. For an AM signal, which is of double sideband full carrier, which is transmitted with an unmodulated carrier power of 100 watts. I repeat, an AM signal with of double sideband full carrier is transmitted with an unmodulated carrier power. So unmodulated carrier power is nothing but your carrier power. So it is 100 watts. That is modulated simultaneously by 3 modulating signals. And the 3 modulating signals are going to have 3 different modulation index. Okay, so the 3 modulating signals are M1, M2, M3, and their coefficients are given as 0.2, 0.4 and 0.5. So these are the modulation coefficients of the 3 modulating signals. So together it is going to get transmitted. So we have to find the total coefficient of modulation. What is the total modulation coefficient? As usual, upper and the lower sideband powers and the total transmitted power. Okay, so this is given. You have to find what is the total modulation index. Then you have to find the upper sideband as well as the lower sideband powers as well as the total power. Okay. So how you find the modulation coefficient? So total modulation coefficient is given by total modulation coefficient MT is equal to root of M1 square plus M2 square plus M3 square. So it is root of 0.2 square plus 0.4 square plus 0.5 square. So it will be 0.04, 0.16 and 0.25. So if you add and take the square root of this, it will be 0.67. And next is you have to find the sideband powers. So what is the total sideband power? It will be total modulation index square into PC divided by 2. So it is 0.67 square into the carrier power is given as 100 divided by 2. Right? Carrier power, carrier power is 100 watts. Substitute this and make simplify. On simplification, anyway, it is 22.5 watts. Check whether you are getting this answer. Make use of a calculator and check your answer. And tell me whether you are getting this. Are you getting it?
Yes, ma'am.
Fine. So what is the second part? Second part is this is the sideband power. The second part is what is going to be the total power. So you know, of course, total power is equal to carrier power into 1 plus. Here instead of taking single modulating signal modulation index, you have to take the total modulating coefficient. So it is 100 watts into 1 plus 0.67 square divided by already we have seen this MT square PC by 2. That is MC into NT square by 2 is available. So 1 plus of that. It is 100 times plus of it means 100 plus of this 22.45. So 122.45 watts is going to be the total power needed for the transmission. Okay. Let me give one more problem. You try by yourself and tell me the answers. An antenna current of an AM broadcast transmitter modulated to a depth of 40% of an audio sine wave. I repeat, there is an antenna current of an AM broadcast transmitter modulated to a depth of 40%. The modulation index is going to be 40% by an audio sine wave is 11 amps. So this is going to be the antenna current, 11 amps. And this current increases to 12 amps. This current increases to 12 amps as a result of simultaneous modulation of another audio signal. This is increased to 12 amps as a result of simultaneous modulation of another audio signal. What is the modulation index due to the second wave? What is the modulation index due to the second wave? Any idea? Here, instead of power, they are dealing with the current. So what is the relation between the total current and the carrier current? Instead of power, it is going to be root of 1 plus MA square by 2. So here, you are going to have the total current given. First, initially, it is 11 amps and then it increases to 12 amps. So what is going to be the carrier current? The carrier current is total current divided by root of 1 plus MA square by 2. So here MA square, MA is given as 40%. So MA will be 0.4. So this is 11 divided by root of 1 plus 0.4 square divided by 2. So 0.4, it is 0.16, 0.16 divided by 2 is 0.8, 0.8 plus 1 is 1.08, 1.08. So take the root of it. It is coming as 1.039. So 11 by 1.039, okay, comes to 10.58 amps. So this is the carrier power needed. So the second part of the question is, what is going to be the modulation index of the second wave. So only when you have the total modulation index, you can calculate the modulation index of the second. So to calculate the second part of the problem, we should know what is the total modulation index due to the first wave and the second. So this is due to the second wave, what happens? It is IT divided by IC square minus 1. Now this current, you take it as the current, increase in the current. Increase in the current leads to 12 amps. 12 amps divided by the carrier current square minus 1. So if you calculate 12 divided by 10.58, square make use of the calculator and do it. Just 12 by 10.58 square. So it comes to 1.1334 square minus of 1. So it is root of point. Okay, it has come to 0.76. So this is the total modulation index. So the total modulation index, we know that it is sum of the squares of the individual modulation index over the root of. So you need first wave modulation index is available. You need the second wave modulation index. So it is mt square minus m1 square. Mt square is 0.76 square minus 0.4 square. Take root of it. So it comes to 646. Fine. So what was given is modulation index of the signal was given, and they say that it is a double sideband AM broadcast system. It has got two currents. Simultaneously, you are going to have two signals being transmitted. One has got 11 amps as a carrier current, another one has got 12 amps as a carrier current. So you should know what is the total current, then only you can calculate the carrier current and the modulation index of the individual system. So first make use of this 11 amps, calculate what will be the carrier current in the case. Second thing, the total current comes to 12 amps. So when it is 12 amps, what will be the total modulation index? So once you know the modulation index of the total, and already in the problem statement they have given the modulation index of the one of the wave as 40%. So you can calculate the other modulation index value. Okay, fine. I think with this we can stop the problem types. Next we'll go and see how we can generate the AM modulated signal. Each and every modulation technique has got two types of minimum generation schemes. Okay. Yeah. Now we'll see what are the AM modulator schemes. So you need a device which is capable of generating all these modulated signals. Now we are going to bother about how to generate an amplitude modulator. So what is amplitude modulation? What do you mean by amplitude modulation? Tell me the definition. What is amplitude modulation?
Varying the amplitude, ma'am.
Varying the amplitude of what? Which signal you are going to vary?
The carrier signal, ma'am.
Carrier signal. We have to vary the amplitude of the carrier signal with respect to what?
Input signal.
Input signal, message signal, or information signal. Okay. So you are going to vary the amplitude of the carrier in accordance to the message signal. Then the resultant signal is going to be the amplitude modulated signal. So to do so, what are all the circuits involved in generating these signals? That we will discuss now. Okay. So you have got AM modulators. AM modulators can be generated by two different methods. One is going to be called as low level modulation, or another one is called as high level modulation. The other name for low level modulation is non-linear modulation, and high level modulation is said to be linear modulation. Under low level modulation, schemes. There are three types of modulation possible: square law modulator, product modulator, and balanced modulator. So these are the three types of modulation techniques. We can generate an AM signal in a non-linear fashion. Whereas under high level modulation, there are two types. One is transistor modulator, another one is switching modulator. Under transistor modulator, depending upon the configuration, you can go for collector or base or emitter configuration. Transistor has got three terminals, emitter, base, collector. So you can choose any one of the configuration in order to produce the ANC. Okay, so obviously we have got 5 types of AM modulation, out of which you have subdivided, classified into low level and high level modulation. All these low level modulation schemes are going to have square law modulator, product modulator, and balance modulator, or the 3 different modulation schemes which can generate an AMC. So these are the methods for generating the AMC. So first we'll see what is low level modulator. So low level modulator, the name says, what is it? It is going to deal with low voltages. The signal which deals with low level of voltages can be used for generating this low level modulated output. So this is used as a non-linear. We are going to bother about the VA characteristics, non-linear region of the VA characteristics of that device. High level modulators are going to get operated in the linear region of the transfer characteristics. Now we'll compare these two. What is low level and high level? Relation between the carrier and the modulating voltage. So voltage level is going to be much more, plays an important role. Carrier voltage is lesser than the modulating signal. Carrier voltage is greater than the modulating signal. If it is V, so VC is less than VM, then it is called as low level modulation. If VC is very, very high when compared to VM, then it is called as high level modulation. Coming to the filtering, heavy filtering is used for extracting the desired modulated frequency terms. Heavy filtering is not required for extracting the desired modulated frequency terms. So that is the advantage of your high frequency modulation, high level modulation. Okay. Coming to the power level, modulation takes place at high power level. In case of low level modulation, we need more power level. Whereas in high level modulation, less power is enough, lesser power level is enough. Coming to the amplifier types, amplifiers like class A, class AB, class B are used, whereas for high level, class C amplifiers are used. Of course, these types of amplifiers have been discussed in electronic circuits too, which are already taken in the previous semesters. Coming to the devices used, these modulators make use of transistors, FET, op-amps, and diodes. Op-amp is nothing but IC741, which you have seen in linear integrated circuits. Or here for high frequency, we go for high power transistors, FET, vacuum tubes. Of course, vacuum tubes are not available nowadays. Coming to the efficiency comparison, the efficiency is going to be lesser when compared to the high level modulating scheme. Where these low level and high level modulators are being used is for wireless telecom system, remote control, walkie-talkies, and in television transmission, we can go for lower transmitters. Whereas high power transmitter broadcasting needs all the signals to be generated in the AM mode to be of high level modulation. How to generate this before? So for generating it, normally we prefer a diode, a transistor, or a FET is used because all these are nonlinear devices. Since low level modulation is otherwise called as nonlinear modulation, we go for a diode or a transistor or a FET as a nonlinear modulation by restricting the operation over the nonlinear region of its characteristics. So we are going to deal with the small signal analysis model, the devices. So the first and the foremost step of AM generation is the square law modulator or power law modulator. Modulation here is done at low power level. The device used as modulators are operated in the nonlinear region of the VA characteristics. So what you need is, you need two signals. One is modulating signal, that is your information signal, and you are going to have the carrier signal. And these are added up together, and this is fed to a nonlinear element. This nonlinear element can be a diode or a transistor or even a FET. The only thing what you are going to do is, you are going to set the operating point. The operating point is set in such a way that it is going to operate in the non-linear region of the devices. So already in electronic circuits 1, you have seen where the operating point has to be fixed. Q point, how to fix a Q point. So you have to design the transistor or diode, whatever it may be, whatever component you choose, in such a way that it is operated in the non-linear region. You have to choose the proper bias voltage VCC. Either you can go for a fixed bias or collector to base bias or voltage divider bias, whatever may be the biasing technique. It is biased in such a way that it is operated in the non-linear region of the characteristics. Then it is put onto the filter, and the filter output is going to be your AM modulated signal. So here the signal at the input of the nonlinear element is considered as V1 of t, and after operating in the nonlinear region, the signal is taking the V2 of t, and at the output of the filter, it is considered as V0 of t. So this way of generating the modulated signal, specifically AM modulated signal, is called as square law modulator or power law modulator. Why specifically square law? We'll see that. So this square law modulator consists of three parts. That is your summer, nonlinear element, and the filter. So the summer is going to add both the signals, carrier and the message signal. Nonlinear device can be diode or BJT or the FET, which is going to be used as an active element, which is operated in the nonlinear region. And coming to the filter can be a bandpass filter. This is used to extract the desired modulated signal. So how we are going to have is, to the input, we are going to have the carrier signal and the modulating signal, VC sin omega CT and VM sin omega MT. So these are the carrier signal and information signal. This is fed to a non-linear element, and this is going to RC filter. Act as a RC filter, which is going to be behaving like a bandpass filter. So you are going to take the output at the bandpass filter as V0 of t. This output V0 of t is nothing but AM modulated signal. So how this behaves is, you are going to apply the message signal and the carrier signal as the input, and it is superimposed with each other and makes the diode more forward bias. It is going to be more positive. So the diode is going to be more forward bias for the positive half cycle of the input signal and less forward bias for the negative half of the input signal. So thus the magnitude of the signal component is going to be greater or more positive during the positive half cycle and less during the negative half cycle. And this is going to result in the modulating signal. So this is your diode characteristic, forward characteristic curve, forward voltage versus forward current. You are going to have the linear operating point fixed here. So the output is going to be the amplitude modulated signal. So this is the envelope of the modulating signal, and this is going to be the carrier of the modulating signal. Of course, analysis, you can go through this derivation part. So this is going to have a carrier signal along with the upper and the sideband frequencies. That is the normal scenario of your AMC. So this VC sin omega CT is going to be the carrier part. VM into VC cos A minus B minus cos A plus B is going to be your, of course, by 2. Instead of that, you can take it as A2. A2 is a constant coefficient. So this is going to be the lower sideband and this is going to be the upper sideband. Okay. Advantages, your bandpass filter you are going to use, and this is going to reduce the harmonics being. But the drawback is the modulator is going to make use of a diode which cannot provide amplification. Only when you make use of a transistor, the signal can be amplified. And a single diode is unable to balance out the undesired frequency complexity. So that is another drawback of using the single diode as a nonlinear device, because it is going to have the undesired frequency completely available. So these limitations can be eliminated by using amplifying device like transistors FET in a balanced mode. So this problem you can overcome by means of another device. You can see they are going to use two transistors, which is going to produce a balanced mode of output, and you have got your carrier signal being given as an input to a transformer primary winding. At the secondary winding is a center tap for having symmetry and balance, and here you are going to feed in the message signal. And this will almost appear like your push-pull amplifier. Remember, one of the transistor will be kept on and the second transistor will be turned on, turned off depending upon the positive half cycle and the negative half cycle. This base emitter region will be forward bias for the positive half cycle, and for the negative half cycle this will be forward bias. So accordingly there will be always an output current flowing through this windings due to the forward half cycle, positive half cycle of the input signal, and due to the negative half cycle of the input signal. This current is taken as IC and this current is taken as IC dash. And this is going to be the bias voltage VCC. This bias voltage will be of sufficient enough in such a way that these two transistors are operated in the nonlinear region of output characteristic curve. Okay. So this balanced modulator circuit of the frequency consists of a frequency mixer, modulator, and a demodulator. So this is going to be, once again, output is getting generated across the secondary primary winding of one of the transformer used at output side is going to be the AM output. Now going to the analysis purpose of the same modulated signal. Base emitter voltage. The base emitter voltage is going to be the carrier voltage plus the modulating signal. So how we are going to apply this? The carrier voltage as well as the modulating signal voltage is going to appear in both the bases of the transistor. This is for the positive of the carrier signal Vc of t, and it is being center tap. It is going to be minus Vc of t. So minus Vc of t will get added with Vm of t, and plus Vc of t will get added with Vm of t at the basis. So Vc of t is Vc sin omega ct, Vm of t is Vm sin omega mt. Of course, this is at the input of the first transistor. At the input of the second transistor, as I said, collector current second half is going to be fed, so negative half cycle. So this will be minus Vc sin omega ct plus Vm sin omega ct. Of course, this Vc and Vm are in out of phase. So what will be the current to the first transistor, and this is the current to the second transistor. Is A1 VBE plus, instead of representing, you are taking it as IC and IC dash, or you can take it as IC1 and IC2 due to the first transistor and due to the second transistor. So these are the two currents, collector currents at the first and the second transistor. So the output is taken at the transformer 2 and the transformer coefficient. It is IC minus IC dash. So here this one is going to be IC and this is going to be in the opposite direction. Output is IC minus IC dash. So K is going to be the constant. IC and IC dash flows in the opposite direction. And this is considered, this transformer is considered as a tuned circuit. This K depends upon the impedance of the circuit. So you can make the substitutions for the collector current as Vc plus Vm square plus A2 into Vc plus T plus Vm the whole square. Just in this formula. VBE plus VBE square. Substitute it, make the simplification. Similarly, this is for the, you will be getting the output voltage. So this is going to be, after subtracting, substitution, cancelling the common terms, this will be the resultant output. So substituting for VC and Vm in this equation, VC is VC sin omega Ct and VC into Vm is VC sin omega Ct plus Vm sin omega t. Substituted, simplify as usual, make use of the trigonometric application. Sin A sin B is cos A minus B minus cos A plus B by 2. This will be your lower sideband part and this will be the upper sideband part and this is going to be the carrier component. So this is going to be your A and B. So of course it has got its own advantages and disadvantages. It is going to be a simpler non-linear circuit, produces undesired harmonics, and this can be eliminated by a band pass filter. But in case of a balanced modulator, the undesired harmonics are automatically balanced and filter is not required. So in the diode, you make use of the filter, band pass filter is used. Since it is a diode, it is going to be a simple circuit. Whereas in balanced modulator, the harmonics are not present. Automatically it is balanced by the making use of two transistors and of course filters. Disadvantages, it is going to produce very low output power level. Hence it is called as a low level. Fine. So these same circuits can be used for generating suppressed carrier AM. The main difference between the full carrier and the suppressed carrier, the carrier part has to be removed. Okay, the carrier part has to be removed in the sense this part has to be removed. Then it will be having double sideband at the expression. How you can remove it? You can remove it by interchanging the carrier and the modulating signal points. That is in this. Here you feed the carrier and here you feed the message signal. Instead of feeding the message signal here, feed in the carrier here and feed in the message signal here. So the carrier will get compressed and the output will have only the double sideband. So this is the other way of generating the double sideband suppressed carrier. You have to interchange the carrier modulating input side and the modulating signal positions where you feed in as a input. Okay. Hope you understood how to generate the AM signal. So AM signal can be generated by means of two modulation levels, low level modulator and high level modulator, or non-linear level or linear level. Now, just now we saw a non-linear level of generating an AM signal by means of a diode as well as a transistor. If it is going to be a diode, it is going to be called as a square law modulator or power law modulator. Or we are going to make use of a transistors, the two transistors is used means then it is called as balanced modulator. In the balanced modulator, the carrier is fed at the primary winding of the transformer. The secondary winding is center tapped and there you are going to apply the modulating signal. If you are going to interchange it, then the same circuit can be used as double sideband suppressed carrier circuit. Okay. I think with this topic, I will wind up today's session.